Okay, hello. Uh, we're looking at ACT Worksheet 212. We will be first looking at probability and the different types of probability problems that will occur on the ACT. And then the second half of this video will explore permutations and combinations, and we'll differentiate between the two. But first, let's look at probability. So probability is something we're probably all familiar with. I'll kind of quickly go over that basic concept, but then I want to kind of touch on these three forms of probability: multiple events and/or situations and expected value. You may be familiar with 0 of them. You may be familiar with all three. All of them do come up on the test. You won't get each one on the same test, but as a whole, about out of 60 problems, roughly 3 problems are going to involve probability, which is these 3 things. And then also among those 3, you'll probably have a combination or permutation problem, which we'll look at as well. In fact, probability and combinations and permutations can make up a total of 4 problems on the test even sometimes. And they're easy to miss if you really just don't know how to go about them. So, and easy enough to get if you do. So we'll just kind of solidify exactly what to do. All right, let's just talk about a standard die with 6 sides, right? So we've got a standard die, 6 sides, labeled 1 through 6 with our sides with the dots, and we roll it. And if it's labeled 1 through 6, the probability of getting any number, let's just say we want number 2, probability of getting a 2 would be 1 out of 6. There are 6 sides. It's always what we want goes in the numerator, and what we're allowed to choose from, or what the whole field is, goes in the denominator. So select from, I'll say. So what you want over what you select from is how you do probability. Again, probably not that difficult, but let's kind of look at these 3. So talking about this die, let's say we're playing a game where I win the game if I roll this number 2 times in a row. So that's a multiple event situation. That's an AND situation. I roll a 2 and I roll a 2 again. So AND kind of pertains to multiple events. So I roll a 2 and I roll a 2 again. Well, the chances of that happening are very slim. It's the chance of the first event happening, rolling the 2 the first time, times if I roll the die a second time, I still have a 1 out of 6 chance of it happening. So that's a 1 out of 36 chance. So if you have, what happens if Dan rolls a 2 and he rolls 1 again? What's the probability of that? You just multiply the first event by the second event. If we change it to an OR problem, and I say, hey, Dan's going to roll the die, he's just going to roll it 1 time, what's the chance he rolls a 1 or a 2? Really simple. I know you know pretty simply it's 2 out of 6, or a 1/3 chance to roll a 1 or a 2. But the official way to do an OR is to add. So an AND is to multiply, and OR probability situation is to add. So it would be a 1 out of 6 chance to roll the 1 plus a 1 out of 6 chance to roll the 2, which gets the 2 out of 6 chance. Okay. The lesser known thing, and you may want to really listen closely for this, is expected value. And if you see a problem like this, it's going to come up usually within the last 10 problems of a test. So let's say we're playing this dice game again, and let's say if I'm going to do a simple version and I'll do a harder version. Let's say if I roll a 6, I get 6 points. If I roll, actually, let's do heads, tails, and then I'll use the die. If I do it, because it will make more sense conceptually. So if I roll heads, not roll, if I flip heads, let's say I get 10 points. If I flip tails, let's say I get 5 points. So if I flip the coin 1 time, my expected value is actually 7.5 points. It's halfway between heads and tails. Although I'll never get a 7.5 just flipping it 1 time, my expected value is the average of the different outcomes. So there's an easy way to do expected value. And I know you say, oh, well, you could just, do 10 plus 5 divided by 2 and get the average of the 2 outcomes. But another way to do an expected value that I find is even easier is you do the number of points for the first event. So heads yields 10 points. you do the probability of it happening, 1/2, plus the number of points for the second event. So the number of points for tails is 0, times the probability of it happening, which is 1/2. And when you add these together, oh, we actually made tails, didn't we make tails 5 points? So when you multiply the probability of happening times the number of points for each event, what you'll get is your expected value. So 7.5, right? 5 plus 2.5. So let's take a look at this dice one. Let's say when we're rolling the dice, if we roll a 6, we get 6 points. If we roll a 1, we get 1 point. What's our expected value if we just do one roll of the die? And each 2 is 2 points, 3 points, 4 points, 5 points. So whatever number you roll, that's the number of points you get. So you have a 1 out of 6 chance of getting 1. So 1 out of 6, 1, plus 1 out of 6, 2, it's a 6. A 1 out of 6 chance in the 3. 1 out of 6, 4, plus, I'll continue it down here, 1 out of 6, 5, plus 1 out of 6, 6. So what's my expected value here? Well, my expected value is 1 6, plus 2 6, plus 3 6, plus 4 6, plus 5 6, plus 6 6. So if we add all that up, so we have 6 over 6 plus 9 over 6, so that's 15 over 6, plus another 6 over 6, so a 21 over 6. And we can divide 3 into each of those, so our expected value is 7 over 2, or just over 3, 3.3. Make sure I added that correctly. That's 6, 10, 15, 21. Yeah, so we have a 3.3 expected value. So that's how you do expected value. You just, for each possibility, you do the chance of it occurring times the expected number of points, and then you add it all together. Okay. So let's kind of take a look at a few quick problems. So this first one, and I'll give you a moment to pause if you want to try it out and figure out what type of problem it is. I am also going to, I'll leave it as it is. Okay. So if Lydia has a standard deck of 52 cards, what is the probability of her selecting 2 consecutive queens, given that she does not replace the card, meaning put it back in the deck after selecting it? So you always want to pay attention to whether or not the card or the marble, whatever it may be, gets put back into the deck or the bag. So she's doing 2 things in a row, and this is an AND situation. And feel free to pause the video if you think you can get this one. But this is an AND situation because we want to select a queen and we want to select another queen. So it's a probability of multiple events. So really, what we're looking at is right here. We have a 4 out of 52 chance of selecting the first queen times a 3 out of 51 chance of selecting the second queen. That reduces to a 1 over 221 chance. So what does that give us? That gives us kind of less than 1% of actually selecting the queen, 0.45 of a percent, less than 0.5%, really. Okay, so now that we are kind of armed with our ability to do all 3 of these, let's take a look at some problems from the test. Okay, so feel free to pause, see if you can figure out what type of problem this is and how to proceed. That's going to be a big part of your skill set when you take this test, is to be able to see a problem, say, oh, this is something I practiced on one of the UES worksheets, and then be able to kind of pause and diagnose exactly how to proceed. So you can try this one right now. I'm just going to keep talking, though. So Tom is in Miss Zhu's class. By the way, this one came up at the end of a test, so it's supposed to be a pretty hard problem. I don't think it's too bad once you know kind of how to do it. To choose 4 students from her class of 24 students to answer questions, Ms. Sue will put 24 cards, each with the name of a different student from her class on it, in a box. So she's going to have 24 cards, all with the names of different individual students in her class. Next, Ms. Sue will randomly draw 4 cards from the box without replacing, so she's not putting any cards back. What is the probability that Tom's card will not be drawn? Okay, so essentially we want to figure out what's the probability that we draw 4 consecutive cards and none of them is Tom. So this is also an end one. We're drawing 1 card and another card and a third card and a fourth card. So it's probability of multiple events. Well, the probability of getting anything but Tom the first time around is 23 over 24. Because we're not replacing the card, the second time around, we have 22 cards that are not Tom's and 23 cards left, right? The assumption is we pulled a card the first time, it wasn't Tom's, right? Because if it was Tom's, then the problem would be over. But we're going for not grabbing Tom's card. So 23 out of 24 chance we grab someone else's card that isn't Tom. There are 22 left that aren't Tom and 23 left in total. Then we pull another card that isn't Tom's. So there are 22 cards left. 20 of them aren't Tom's. Then we pull another card that isn't Tom's. 21 cards left, 20 of which aren't Tom's. So then when we multiply this out, there's a 20 out of 24 chance that we, 4 consecutive times, we pull a name out of this box and it's not Tom's. What does this reduce to? This reduces to 5 over 6. So our answer here is D. Okay. Okay, here's an expected value problem. Again, I would encourage you to kind of pause the video and try this one. I'm going to keep on going though. So at the school carnival, Anna's playing a game involving a stack of 10 index cards. Each card has a single number written on it. 1 card has a 1, 2 have a 2, 3 have a 3, and 4 cards have a 4. Anne will choose 1 card at random, and she will be awarded the number of points equal to the number written on the card. Let the random variable x represent the number of points Anne receives on any one draw. What is her expected value? There's our key word. So what value does she expect of x? So here's what we know. She's going to just pick 1 card and she'll get the number of points on that card. What would we expect? Well, we know exactly how to do this. We take the chance of pulling a 1. So first off, we have 10 cards. The chance of pulling a 1 is a 1 out of 10 because only 1 card has a 1 on it. And that card is worth 1 point. So I'll kind of go point, and then this is probability. Or, probability. I'm not going to label it the same for the rest. You kind of see this diagram or this setup right here. So then, when it comes to 2s, that's 2 out of 10 cards. And if she draws a 2, it's worth 2 points. That's not times. It should be plus for expected value. I'm adding up the values. All right. So then, if she draws a 3, she'll get 3 points, and it's a 3 out of 10 chance. And a 4 is worth 4 points, and it's a 4 out of 10 chance that she draws a 4. So 4 points. So we want to know what's expected value when Anne plays this game. So let's see. So this is 1/10 plus 4/10 plus 9/10 plus 16/10. So what we're looking at here is 5, 14. 14 plus 16 is 30 over 10. So Anne should expect 3 points when she draws a card. So if they say to Anne, hey, Anne, do you want to play this game? You win if you draw a value greater than 3. Anne should say, no, I don't want to play the game because my expected value is 3. So if I win, if my value is greater than or equal to 3, not equal to, just greater than 3, then I don't want to play the game because my expected value is 3. So chances are I'm not going to win. I love probability. It's really fascinating to me because I like playing all types of games related to probability, card games and things like that. And I also like watching sports and trying to figure out the probability that a team will win. Anyway, each of 100 distinct playing cards, and you'll try to figure out what type of problem this is. And feel free to pause right now if you want to just try the problem on your own. But I'm going to keep on going. So each of 100 distinct playing cards is one of 5 solid colors and is numbered with 1 integer. There are 20 each of blue. So I'll go blue, red, we have yellow. Funny thing is I'm writing this in purple. I always find that trippy. Blue, red, yellow, green, and orange. And these are all numbered 1 through 20. One of the 100 cards will be selected at random. What is the probability that the selected card will be blue or 17? So this is an or problem, which means we're going to be adding. So blue, we have 20 that are blue. We will take if it's blue, or we'll take if it's a 17. So red is going to have 117, right? If we label the cards 1 to 17. So it will have 117. Yellow will have 117. Green will have 117. Orange will have 117. The thing to be really careful, so your answer is pretty simple. We add these together, and these aren't the number 17. That represents card 17. These are all just one card. So it's really 20 plus 1 plus 1 plus 1 plus 1. So the chance of getting either blue or a 17 is going to be 24 out of 100. The mistake a lot of people make is they go with E. They go, oh, there are 5 17s, because there's also a blue 17, and there are 20 blues. So they go, oh, 20 plus 5 17s, 20 blues plus 5 17s. But you got to be a little more careful than that. 17s, 5. Why? Because if you do this, one of the 17s is a blue 17. And the blue 17 can't count for 2 cards. It's just 1 card. So we already counted the blue 17 when we counted the blues. So that's why we didn't. That's why we only have 24 cards that we can get, and not 25. Okay. Hopefully that makes sense. I'm gonna. Yeah, 22 is a quickie. You can pause it and try it. See if you get it. It came towards the end of a test. It's if you're disciplined at your end versus or, I think you'll be able to figure this one out. But I'll give you a moment to think if you pause the video. I'm going to keep on going. The probabilities that each of 2 independent events will occur are given in the table below. What is the probability that both events A and B will occur? That is A and B. So this is an AND problem, meaning that you're going to multiply. The mistake people make is they think, oh, it looks really clean. The possibility of A and B happening is going to be 0.6. It's going to be E. No, that would be if we're happy with either A or B occurring. Then we would add. But the possibility of both event A happening, which is a 1 out of 5 chance, and this is a 2 out of 5 chance. This bottom one, right, this is 1 out of 5. This is 2 out of 5. So the possibility of both of those happening is reduced, right? It's harder for 2 things to happen than just one of them to happen. So that's why end is always lower. So anyway, this is 2 out of 25, which is really 8%. If we multiply this by 4, it's the same as 8 over 100, or 8%. Okay, so that's the first half. Let's quickly go through the second half. So permutations. A lot of people don't necessarily know how to do these. They are very easy once you do know. So a permutation would be, I'll give you an example. I have 3 friends and they want to get in line for a picture, and they want to know all the different ways they can line up for a picture. So if each way I order them counts as a different output that we care about, then we're talking about different, distinct, or unique ways. We're talking about a permutation. What do I mean by that? I mean, with 3 friends, they could be A, B, C. That could be one order. They could be A, C, B. They could be B, A, C. They could be B, C, A. Or we could line them up C, A, B, or C, B, A. So although it's only one group, there are 6 different, distinct, or unique ways we're able to arrange these friends. A permutation is always going to be higher than a combination because a permutation cares about every unique way. The way you set up a permutation is really simple. So for this friend scenario where we got 6 possible outcomes, What you do is you always put out a space every time you have to make a decision. So we're putting out 3 spaces. We have to decide which friend stands here, which friend stands in the second spot, and which friend stands in the third spot. Then all you do is you put the number of options available above each space. So for this first spot, we have 3 friends we can pick from. We picked friend A, supposedly. Then the second space, we have 2 friends left to pick from. And then the third space, we have 1 friend left. 3 times 2 times 1 gets us 6. So this is textbook how you would do any permutation. Just put out the spaces, options above each space, multiply it out, and you'll have your answer. And it will help you kind of think through specifically what you know and what you don't know. By the way, another way to write this is to write 3 exclamation mark. What that actually means is 3 factorial. Factorial means multiply the integers down to 1. So 3 times 2 times 1. 5 factorial would just be 5 times 4 times 3 times 2 times 1. Okay. So here's an example. And feel free to pause and try out this example right here, this King's Head Pub one. I'm going to keep on going. So 7 bands want to play. And I'm actually going to zoom out because I want you to be able to see the process. Right? I still want you to be able to see the 3 steps for now. So here we go. We got the 3 steps here in this problem. So see if you can apply these to the problem. So 7 bands want to play at the King's Head Pub. Beth, the manager, only has enough time to allow 3 bands on stage. And how many different orders? So we care about all the arrangements or all the distinct ways. How many different orders can she arrange the 3 bands? So we care about who plays first, second, and third. So what we have to do is Beth has to make 3 decisions. She has to decide who plays first, who plays second, and who plays third. It's not as simple as 3 factorial, though, because if you read carefully, there are 7 bands that want to play. So really, if we think about it, how many options do we have for the first space? We have 7 bands we can pick. We picked one of the bands, so now we have 6 bands left. And then finally, we have 5 bands left for the last spot. So this is going to give us 30 times 7. This is going to give us 210 different ways we can arrange these bands. So let me show you the combination part of this. So it's the same problem, just slightly tweaked, okay? And a combination is, well, I'll explain what it is as we do this problem. So Beth at the King's Head, by the way, permutations, far more likely than combinations on the test. Combinations are a little bit of, I wouldn't call them a unicorn, but they're much more rare than permutations. You're very likely to get 1 permutation when you take this test. If you get a combination, that's maybe like a, I don't know, less than 20% chance that that comes up on the test. But you want to know how to do both so that no matter what type of problem you get, you feel comfortable. So anyway, combination is easy enough. I'll show you. Beth at the King's Head decides she doesn't really care about which band plays first, second, or third. She only cares about how many different groups of 3 bands can play from the 7 bands. How many different groups are possible? So in other words, Beth doesn't care if A, B, C, what order the band's playing. So she doesn't care if it's A, B, C, A, C, B, B, A, C, B, C, A, C, A, B, and C, B, A. This does not count as 6 outputs for her. She does not care about the order. This is just one group. So if Beth doesn't care about the order, we're not going to get a number as high as 220. We just want to know how many different groups. We don't want to know all the different arrangements of orders. So we do start off just like a permutation. What we do is we put out the spaces and we have to make 3 decisions. We have 7 options for the first band, 6 options for who plays second, 5 options for who plays third. Here's the part that makes this into a combination, not a permutation. It's the denominator. So what we have to say to ourselves is we don't want to count one arrangement of 3 bands 6 separate ways. It's just one group. So you always take the number of spaces on the top and you put the same amount of spaces on the bottom. So in this case, 3. But instead of counting down from 7, you just count down to 1. So it's just 3 factorial. So if we had just 7 times 6 at the top, for example, if we were just choosing 2 bands, it would just be 2 factorial on the bottom. So in this case, we still get the 210 on the top, but we divide it by 6, which means that in this case, 210 divided by 6, we're just looking at 35 different groups. So although we can arrange the groups 210 different ways, it's really only 35 groups. And that's when it becomes a combination problem. Let's just look at two problems from past tests. So this one I picked on purpose because there's some notations that I'm going to need to explain. I'll explain it real quick. So the Beth problem with the King's Head pub, when we had 7 bands and only 3 spaces. Well, if you do that as a permutation problem, it's 7 options, pick for 3 spots. So the higher number always goes in the front, right? You're always going to have more options than choices. If it's a combination problem, we would have 7 bands to choose from, and we would choose for 3 spots. So the spots always goes in the back, and the choices has to be more than your spots. So anyway, feel free to pause the video and see if you can get this one. I'm just going to keep on talking. A committee will be selected from a group of 12 women and 18 men. The committee will consist of 5 women and 5 men. Which of the following expressions gives the number of different committees that could be selected from these 30 people? Okay, so really this just comes down to figuring out, is this a combination problem or a permutation problem? Well, let's do the women first. So if we're looking at the women, we have 1, 2, 3, 4, 5 spaces. We're going to make 5 decisions. We have 12 women to select from, 11 women to select from, 10 women to select from, 9 women to select from, 8 women to select from. So the question becomes, do we care about all the different ways to arrange these women? Do we care about in what order they sit in? And the thing is, we don't. We just want to know how many different groups. So this is just a simple combination problem. So that means on the bottom, on this one, we would actually have to have a numerator, and we would do a 5 factorial. Right. It's a combination problem because we don't care about the order in which the women sit. We don't care about who goes where. We just want to know how many different groups. So knowing that, looking for the women, we see 12C5, and then the men, we have 18 men, and we're choosing for 5 spaces. So this one's just going to be A. Okay, one more problem. And again, pause it. Give it a shot if you want to. This one was one of the final 10 problems on the test. So if you get it, you should feel pretty happy. No pun intended. Anyway, Happy Soup Company stamps a 6-character product code on each can of soup it produces. Each product code consists of 5 letters from a 26-letter alphabet followed by a single digit. The letters may repeat. That's a big deal. How many such product codes are possible? So again, we got to go through the steps, right? The first step is to put a space for each decision. The second step is to put the options above each space. And you can pause right now as well if you want to try it from here. So if we think about it, we have to make 6 decisions. We have to pick 5 letters, and we have to pick a number. So we can repeat the letters. So it's 26 options, still 26 options, because I could do A, yep. And then 0 to 9 for digits. Be careful, that's 10 digits. How do I know that? Really simple. You take the difference and add 1. 1 to 3 is 3 digits. It's not 2, right? We have 1, 2, and 3. 0 to 9, if you want to count it on your fingers, that's 10 digits. So really, we're looking at 26 to the 5th power times 10. Okay, I hope this video is helpful. Good luck on this worksheet. Like I said at the outset of the video, out of 60 problems, you're going to get 3 to 4 that are going to involve skills that you're practicing on probability, combinations, permutations, 212. So good thing to sharpen up those skills now. All right, good luck.